All right, hello everyone. So in this video we're going to be doing 1.5. Okay, there was a 1.5 intro. That was the previous video. Now we're doing 1.5. Okay, this is about electrons and how they're arranged around the nucleus. So I just want to show you a couple things that are not in your packet, just to look at. Okay, this is not in your packet. Just want to show you. So you may have kind of traditionally learned what we call the Bohr model of the atom, where there's a nucleus in the middle, and then there's these energy levels that we represent as circles or rings, that show the energy levels, okay? The first energy level can hold 2 electrons. Once you have 2 in the first level, then you move to the second level, which can hold 8. Once you have 8 in the second level, you move to the third level, which can hold 18. Fourth level can hold 32. And then it gets even bigger after that to 5th, 6th, and 7th level. And we generally have, in lower level science classes represented the electrons with dots. Okay, so this hydrogen has 1 electron, we filled in 1. Element number 2, helium, has 2 electrons, we fill in 2. Okay, lithium element number 3 has 2 in the first level, 1 in the second level. Beryllium, 2 in the first level, 2 in the second level. Okay, 2 and then 3, 2 and then 4, 2 and then 5, 2 and then 6, 2 and then 7, 2 and then 8. Okay, so this says 2 in the first level, 8 in the second level. And remember, the outermost energy level is what we call the valence electrons. Okay, and then once you'll notice every time a level fills, it's at the end of the row, and then we go down to the next row. Okay, rows are called periods. Okay, so periods are so we filled up the first energy level in the first row. Then we move down to the second row, and we start filling the second energy level. Okay. These numbers in the box are just the atomic number. Okay, so that's the number of electrons. And then these are the period numbers, or the numbers for the rows. Okay, so you'll notice every time we start a new row, we're adding on a new energy level. So that's why the periodic table is arranged the way it is. So that every time you start a new row, you're putting an electron in the next highest energy level. Just like on a calendar, we start a new week with every row. The periodic table, we start a new energy level with every row. So you can see the first period, the first row has 1 energy level. The second period, the second row has 2 energy levels. The third period, the third row, they all have 3 energy levels. And the fourth period or the fourth row, they have 4 energy levels. Okay, and you'll notice I stopped at element number 20. Okay. Also, the reason why this looks a little different from a typical periodic table is I kind of consolidated it a little bit. Normally there's this big space between element number 4 and 5 and element number 12 and 13. I kind of consolidated a little bit and stopped at number 20. Okay. The reason I stopped at number 20 is because after electron number 20 is when the energy levels start to fill out of order. Okay, it doesn't go 2 in the first level and then 8 in the second level, then 18 in the third level, and then 32 in the fourth level. It starts out normal, 2 in the first level, 8 in the second level. The third level you only put 8 in, and then after you put 8 in the third level, you jump up to the fourth level and put 2 in, and then you go back and add the remaining 10 to the third level, and then you go up to the fourth level and you add some more, and after that things start to feel very out of order. Okay, it doesn't just go first, second, third, fourth. Okay, you'll get to a point where you're putting electrons in the 6th level, and then you got to go back to the 4th level, and the reasons for that are just that there's certain sub-levels within each level with different energies that don't always kind of follow this linear pattern that we might expect. So up until element number 20, things go pretty smooth, and then things start to fill out of order. And like I said, that's because of sub-levels that we're going to talk about. So sub-levels are not something we worry about with these basic electron models, but they are something we worry about with higher level chemistry. Okay, so electrons are not actually in these, electrons don't exist in these circular paths. Okay, we draw them that way just because it's easier to draw the energy levels, but the energy levels are not fixed circles. Okay, they used to think that 100 years ago. They thought the electrons were in these orbits. They're not. Okay, what we know now is that electrons are in orbitals. Orbitals are not circles. I hate the word orbital because it sounds like a circle. It's not. Okay, it's not a circle, it's not a sphere. Okay, an orbital is a 3-dimensional region of probable location where an electron is likely to be found. Okay, and they have all different shapes. So I know you hear orbital and you start picturing circles. Circles are orbits. We don't believe in those anymore, even though we sometimes draw it that way to make it easier. Orbitals are three-dimensional regions of probable location. So that's what electrons are located in. And the electrons in the orbitals, their location is designated by something called quantum numbers. So every electron in an atom has 4 quantum numbers. The first one tells you the energy level it's in, or the shell. The second one tells you the sub-level, the energy sub-level that it's in, or the subshell. And the third and fourth tell you things that are more specific about its location that you don't need to know for AP chemistry, okay? So all you need to know for AP chemistry are the first quantum number, which is the principal quantum number, which is essentially the energy level. So if it's in the first energy level, we call it n equals 1. If it's in the second energy level, n equals 2. If it's in the third energy level, n equals 3. Generally, we go up to about 7 energy levels, okay? Our biggest atoms that we know about that are on the periodic table have 7 occupied energy levels. That's why your periodic table has 7 rows on it, okay? These all have 1 occupied energy level, 2, 3, 4, 5, 6, and 7 occupied energy levels, okay? So the first quantum number essentially tells you the energy level, or the shell, okay? So for this electron, n equals 1. It's in the first energy level, okay? Let's see. Let's say this electron right here, n equals 3. It's in the third energy level. That's the first, that's the second. So for this one, n equals 3, right? For this electron, n equals 2. It's in the second energy level. But for this electron, n equals 1. It's in the first energy level, okay? The second quantum number, this is not a 1, it's a lowercase l. So you could just write it like a cursive lowercase l, okay? So the second quantum number is the sublevel, okay? What you may have learned in the past is that the sublevels are given letters, okay? So again, this is not in your packet. It's just a way that I've written it out in the past that I think is kind of helpful. So when your principal energy level is 1, there's only the S sublevel. When your second energy level, there's 2 sublevels, SP. Third energy level, there's 3 sublevels, SPD. Fourth energy level, there's 4 sublevels, SPD and F, okay? So they gave the sublevels letters, okay? We can also give them numbers, which is a little confusing. So for a given energy level, the sublevel ranges from 0 to 1 below the energy level, if that makes sense. So in the first energy level, there's only S, okay? So for the first energy level, L equals 0, that means there's an S sublevel, okay? For the second energy level, L equals 1, that means there's an S and a P, okay? For this third energy level, L equals 2, there's an S, a P, and a D. Fourth energy level, L equals 3, there's an S, P, D, and F. So you might be wondering, well, if there's 1 sublevel, why do we call it a 0? Or if there's 2 sublevels, why do we say L equals 1 when there's S and P, okay? It's just kind of weird. Don't overthink it too much. It's just because we consider S not to be a sublevel. I don't know. It's more like once you have S, then these are considered sublevels. Okay. I feel like that is very confusing. Don't stress out over this if you're not totally following me. Okay. Don't worry too much about knowing the numbers. Just remember, first energy level has S, second energy level has SP, third energy level has SPD, fourth energy level is SPDF. Okay, and we're not really going to go much above the fourth energy level for today's lesson. Okay, last part you can cross that out. I don't really even understand that last bullet point. Okay, the third quantum number and the fourth quantum number, you could just totally cross that out. If you want to read it, you can. You'll learn more about that if you take upper level chemistry in college. For our purposes, you just need to know the first quantum number is the energy level. The second quantum number corresponds to the sublevel. Okay, S, P, D, F, whatever. Okay. The Pauli exclusion principle, that actually reappears on a later page, so I'm going to hold off on talking about that right now. So how many orbitals and electrons can you have in each subshell? A subshell is a sub-level, okay? So we have the S sublevel, the P, the D, and the F, okay? The S sublevel is often represented by just one box or one line. In chemistry, you may have done boxes or lines. And then the arrows represent electrons, okay? We normally represent electrons with dots, but when we're talking about quantum numbers and stuff, we often represent them with arrows. So next to the S, there's one orbital, okay? I want you to draw one line, okay? That line represents where we can like indicate that there are two electrons. Just don't put anything on the line, just one orbital, okay? P has 3 orbitals, draw 3 lines. D has 5 orbitals, draw 5 lines. You can probably see a pattern here. F has 7 orbitals, draw 7 lines. Okay, I know this feels a little bit abstract, you just got to roll with it. It's not actually as hard as it seems, okay? So in chemistry, if you took chemistry with me, I often represented them with boxes instead of lines. But an S sublevel or subshell has 1 orbital. P has 3, D has 5, and F has 7. And then the maximum number of electrons, you can put 2 electrons at most in each blank, in each orbital. Okay, so that means the S sublevel can hold 2 electrons in that line. The P can hold 6 electrons. The D can hold 2, 4, 6, 8, 10 electrons. And F can hold 2, 4, 6, 8, 10, 12. Whoops, did I not draw 7 lines here? Sorry. 2, 4, 6, 8, 10, 12, 14 electrons, okay? For each sublevel, okay? So let's back up and look at the principal energy level, the shell, the main energy level, all the subshells within that, and then the total number of orbitals and the maximum number of electrons that can fit in that shell, okay? When n equals 1 in the first energy level, for the first energy level we would say L equals 0, okay? It does have a subshell. We just don't consider it subshell because there's only one of them. I don't know. Okay, but in any case, it's an S. Put S in parentheses. For n equals 2, second energy level, L equals 1. For n equals 3, L equals 2. And for n equals 4, L equals 3. Okay? So when L equals 0, that means you only have an S sublevel. When L equals 1, that means you have an S and a P. Okay? The 1 meaning P is considered the sublevel, whereas S is kind of not considered sub. I don't know. For L equals 2, we have S and then P and then D. And for L equals 3, we have S, P, D, and F. Okay? I like the way I drew it here better. Okay? So I just think you can see it more clearly. First energy level, you just have F, S. Second energy level, you have S and P. This and this. Okay? Third energy level, you have SPD. Fourth energy level, you have SPD and F. So you can see the principal energy levels are getting bigger and bigger and bigger as you get further and further from the nucleus. They can hold more and more electrons, okay? So the first energy level, because it only has S, it can only hold 2 electrons. Oh, let me back up. The total number of orbitals, sorry, is just 1 here, because S only has 1 box or 1 line, okay? The second one has S and P. S is 1, and P has 3 lines for a total of 4, okay? So if you remember, S has 1 and P has 3 for a total of 4. The third energy level has SPD. So we have 1 plus 3 plus 5 orbitals for a total of 9. And the fourth energy level has SPD and F. It has all of these, okay? So 1, 3 plus 5 plus 7, okay? What does that add up to? 9, 16, okay? Orbitals, okay? Remember, orbitals are the lines. Again, people keep thinking that orbitals are like circles or spheres or something like that. We represent them with lines. Each of these lines is an orbital, okay? Each of these lines is an orbital. It's representation for a region where an electron's likely to be found. They are obviously not actually, they don't actually look like this, okay? But it's so hard to draw orbitals because their shapes are all different. It's just easier to put these lines where we fill in electrons, okay? So the maximum number of electrons for the entire energy level, okay? Remember, each orbital can hold 2. So if there's one orbital, it can hold 2 electrons total. If there's 4 orbitals, it can hold 8 electrons total. 9 orbitals means 18 electrons, and 16 orbitals means 32 electrons. So this means that the first energy level can hold 2, the second energy level can hold 8, the third energy level can hold 18, and the fourth energy level can hold 32, okay? And that's what I was saying at the beginning when I was showing you this paper. This is not in your packet, but when we were talking about this 2, 8, 18, 32, okay, now you can see these electrons in those energy levels are distributed over a variety of sublevels and orbitals, okay? So I want you to skip down to the bottom here. I just want you to cross this stuff out. This M is the third quantum number. You don't need to know M for AP chemistry, so just cross all that out, okay? So what we have here is an orbital diagram. Again, notice there's no circles. A lot of people hear orbital diagram and they start drawing this. Okay, this is not an orbital diagram. This is what we call a Bohr model, because Bohr was the scientist who thought that electrons moved around the nucleus in circles. We know that's not true anymore, even though we sometimes draw it that way for simplicity's sake. This is an orbital diagram, okay? So what it did, it took all the sublevels and arranged them in order of increasing energy, okay? So the number is the principal energy level and the letter is the sublevel, or the subshell. So you could say the 1 is the shell, the S is the subshell, or you could say the 1 is the energy level, the S is the sublevel, okay? And what it did was arrange them in order of increasing energy, okay? So in order to figure out where the electrons are, you just work your way up, okay? So you fill 1s, then you fill 2s, then you fill 2p, because that's the next lowest down. Then you fill 3s, then you fill 3p, and then look carefully at which one's lower down, 4s or 3d. You'll notice 4s is slightly lower, so we fill that, then we fill 3d, then we fill 4p, 5s, 4d, 5p, and then 6s, 4f, okay, 5d, 6p, I think the next lowest is 5f, and then 7s I think is lower, and then 6d, 7p. So you can tell the energy levels get closer together in energy as you get further from the nucleus. So at first it's very easy to tell what's next, and then it gets a little murky, okay? So you can basically just trace your way up if you know the number of electrons to figure out where they're arranged. So let's say we wanted to draw the orbital diagram for, let me just pick an element here, zirconium, number 40, okay? So what I would do is I would just start placing my electrons, okay? So we have 40 electrons to work with. The first 2 are in the first energy level. Just draw 1 arrow up and 1 arrow down, okay? And then we move to the second energy level. We'll do fill 2s, 1 up, 1 down, and then we'll move on to 2p. When you have multiple orbitals in a sublevel or a subshell, put 1 electron in each blank before you double up. Okay, put one each. It's like people on a bus. They want their own seat before they're forced to double up. So you'll go 1, 2, 3, and then you come back and double up like that. Okay. So you'll notice we have 2 electrons in 1s. That's the first energy level. We have a total of 8 electrons in the second level. 2 of them are in 2s and 6 of them are in 2p for a total of 8. Okay, which we expected. We know that 2 electrons can go in the first level and 8 can go in the second level. Now let's move on to the third energy level. 3s, 1 up, 1 down. 3p, 1 up, 1 up, 1 up, down, down, down. Okay. And then it might be tempting to go on to 3D because you want to finish filling the third level. But notice part of the fourth level is lower down than this part of the third level. So we have to fill this one next. Okay. And then we can go to 3D. Up, 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 and then down, 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 down. And that's why when you look back at this paper, this is not in your packet, this was just one I was showing you. This is why the 19th and 20th electrons go in the fourth level, even though the third level is not full yet, right? So for potassium and calcium, there was still space in the third level, but I jumped up and put one in the fourth level, okay? And then the 20th electron also went in the fourth level. And then if we were to continue, we would go back to the third level, okay? That's what we see happening right here. We put 2 in 4s because it's lower energy than 3D. Then we go back and fill 3D, okay? So let's just stop and see where we're at here. I know we have to get to, we're doing zirconium, which has 40 electrons. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, okay? 31, 32, 33, 34, 35, 36. You can just do a half arrow instead of the whole arrow, just it's quicker to draw, okay? So we're at 36, okay? 5s is the next lowest down, 37, 38, and then we move on to 4d. Remember, you've got to put 1 in each box, in each orbital before you double up. So you got 39 and 40, and you're done, okay? If you had accidentally written these two in the same orbital, it would have been counted wrong. So you might be saying, well, why do I got to put 1 in each box if I'm just going to double up? Well, sometimes you end up not doubling up because you run out of electrons, okay? So this is zirconium, Zr, because it has 40 electrons, okay? So be sure you put 1 in each box before you, or 1 in each blank before you double up. So that's the electron configuration for zirconium, or I should say the orbital diagram, okay? If we were to take this and write an electron configuration, we would start with 1s, and we would write the number of electrons as a superscript, okay? We don't want to call that an exponent because it's not 1s squared. Scientists say 1s2, we just know that we put that 2 up high, and that represents the number of electrons in that sublevel or subshell. Then we have 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 2, 4, 6, 8, 10, 4p6, 5s2, 4d2, and then we stop, okay? So a good way to double check, and this is what we call electron configuration, okay? So this is orbital diagram, this is electron configuration. And if you want to double check, just add up the superscripts and be sure they add up to 40, okay? Count up your arrows, be sure they add up to 40, because zirconium has 40 electrons. Its atomic number is 40, okay? All the electron configurations we are doing right now are ground state, okay? Which means the electrons are in their lowest possible configuration. Excited state is what happens when an electron absorbs energy. Like we talked about valence electrons absorbing light and jumping up to higher energy levels. So an excited state electron configuration might show, you know, these valence electrons up here, okay, instead of down here where they should be. But for now, we're just doing ground state, where everything's in its lowest energy. Yeah, that's why we start at the bottom and work our way up, okay? And that's called the Aufbau principle, the principle that the lowest energy sublevels fill first, which is why we start at the bottom, okay? So that's called the Aufbau principle. It just means you start at the bottom, okay? Lowest energy fills first, and then you work your way to higher and higher energies. And you can see things start to fill out of order. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. So things start to fill more out of order the higher you get. The Pauli exclusion principle says that each orbital can only hold 2 electrons at most, and they have to have opposite spins. The spin, it's not a literal spin, it's a quantum world spin. It's hard to explain what it is. I don't fully understand it, but it just means you have to have 1 arrow up and 1 arrow down, okay? So if you saw an electron configuration with 2 arrows up in one orbital instead of 1 up, 1 down, that would violate the Pauli exclusion principle. Then we got Hund's rule. Hund's rule is basically the one saying that you need to put 1 electron in each orbital before you double up, okay? So when electrons are placed in a set of orbitals of equal energy, you know, in one row, they are spread out as much as possible, okay? So that's why you're going to put one in each orbital before you're forced to double up. That's Hund's rule, okay? So we were following those rules when I was filling out the orbital diagram, but I just want you to know the name of those rules. Okay, so what we're going to do now is practice, okay? So you could, I'll do the first one and then you can try the rest on your own. So complete an energy level diagram, or we call it an orbital diagram. For each of the following elements, add electrons to orbitals following these three rules, okay? So carbon, if you look on your periodic table, it has 6 electrons total, okay? So we start at the bottom, 1, 2, 3, 4, 5, 6, and we are done, okay? The outermost electrons, I'm going to have you circle them, okay? These electrons in the second energy level are the valence electrons, okay? Those are the electrons in the outermost occupied energy level. If we were to look at the Bohr model, again, this is not in your packet, the Bohr model for carbon looks like this: 2 electrons in the first level and 4 electrons in the second level. The ones I highlighted are the valence electrons. Now we know those 2 electrons in the first level are in 1s, and in the second sublevel, 2 of these are in 2s and 2 of them are in 2p. Okay, so we have a more kind of detailed view on how these electrons are arranged now. So these are the 2 in the first energy level, the first ring, and these are the 4 in the second energy level. Some of them are in 2s and some of them are in 2p. Okay, so you can pause the video and go ahead and try magnesium, chlorine, and vanadium on your own, and then unpause the video. Okay, so magnesium is element number 12. So it has 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we're done. Okay? I want you to circle the ones in the third energy level. Those are the valence electrons. Okay, those are the valence electrons. So it has 2 in the first, 8 in the second, and 2 in the third. Okay, and if we look at this Bohr model, that's exactly what we had here. 2 in the first energy level, 8 in the second energy level, and 2 in the third energy level. All right, chlorine. Chlorine, if you look at your periodic table, it has 17 electrons. Okay, so we'll put 2 in the first level, 2s, 2p, up, 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 down, 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 3s, 3p. Let's see where we're at before I finish filling that. 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, and we're done. Okay. Again, all the electrons in the third energy level that start with 3, those are your valence electrons. Okay. And as you can see, if we were to draw the more simplistic Bohr model, we have 2 electrons in the first level, 8 in the second level, and 7 in the third level. Okay, so in that third level, the valence electrons, 2 of them are in 3s and 5 of them are in 3p, for a total of 7. And then D, vanadium. Vanadium is element number 23. Okay, so we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay? This is supposed to have more lines. Maybe they knew we weren't going to be... Oh, I think there was just got cut off. D sublevels have 5 orbitals, so there should be 5 lines like there are here. With this one, the valence electrons are a little bit more confusing. It technically has 2 valence electrons, but because these are so close, sometimes these slide around and they all act like valence electrons. So I'm not going to have you circle valence electrons for this one. Okay. Groups 3 through 12, groups are the columns. So this kind of lower down area right here, the valence electrons are a bit vague. for reasons why we'll learn later. So I will never really ask about valence electrons for groups 3 through 12 because it can change and there's a lot of variation, things like that. Valence electrons for groups 1, 2, and 13 through 18 are very clear, okay? And the number of valence electrons you may have noticed corresponds to the group number, okay? So everything in group 1 has one outermost energy, one electron in the outermost energy level, which is what we mean by valence electron, okay? So on this, I'm going to highlight the valence electron. This has, hydrogen has one valence electron, lithium has one, sodium has one, and potassium has one, okay? So if it's in group 1, it has one valence electron, and then the period tells you what energy level it's in. So if it's in group 1, period 3, you know it has one valence electron in the 3rd energy level. If it's group 1, period 4, you know it has one electron in the 4th energy level. And that pattern goes all the way down, okay? Francium is going to have one valence electron in the 7th energy level, okay? Group 2, these all have two valence electrons, okay? And then that pattern goes all the way down. Skip all the way over. There's a break here where we're skipping all the way to group 13. We're going to skip all the way to group 13. Group 13 has 3 valence electrons, okay? 1, 2, 3. 1, 2, 3. Group 14 has 4 valence electrons. 1, 2, 3, 4. Group 15 has 5. Group 16 has 6. Group 17 has 7. Group 18 has 8, with the exception of helium. Okay, helium's a little weird because it only has the 1st energy level and it can only hold 2. But everything else in group 18 has 8 valence electrons. And again, that pattern goes all the way down the periodic table for groups 1 and 2 and for groups 13 through 18. Okay, so you can always kind of double check if it's in group 1, 2, or 13 through 18. You can always kind of double check your orbital diagram, look at the valence electrons, be sure it corresponds to the column, okay? I know chlorine is in group 17, okay? Chlorine is in group 17, so it's going to have 7 valence electrons. And look right here, 2, 4, 6, 7, okay? All right, and then, let's see, okay. Sometimes you will not always have an orbital diagram to trace, okay? It's really nice if you have one of these to look at and you can kind of work your way up. So if, let's say something has 21 electrons, okay, and I want to know the electron configuration, I don't even have to draw the arrows. I can just kind of trace my way through until I get to 21. So to get to 21, I know I do 1s2, 2s2, 2p6, that adds up to 10, 3s2, 3p6, 4s2, that adds up to 18, and then 3d1 would be my 19th electron if I was trying to get to 19, okay? So having this is very handy to trace your way up. You don't always have this though, okay? But luckily, this order is kind of hidden in the structure of the periodic table. So just like I traced my way up the orbital diagram to figure out the electron configuration, you can actually trace your way across the periodic table to figure out the electron configuration, okay? Because like I said, the first period represents filling the 1st energy level, okay? That's why the first period only has 2 elements, an element with 1 electron and an element with 2 electrons, okay? So this represents 1s1, this is 1s2, okay? After you do 1s2, the 1st energy level is filled. We got to go to the 2nd energy level, okay? So this represents 2s1 and 2s2, okay? After 2s is filled, then we go to 2p, and each of these represents an electron filling in p. Remember, p can hold 6 electrons total, okay? 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Once 2p6 is filled, then you go to the 3rd energy level. So you go to the 3rd row. 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Then we go to the 4th level, 4s1, 4s2, okay? Now something strange is going to happen. Remember, after 4s, we go to 3d, okay? So as soon as we cross into the d block, it's going to go one level behind the d block. We call this the S block because these all end in S1 and S2. We call this the P block because these end in P1, P2, P3, P4, P5, or P6. We call this the D block because these are all going to end in D1 through D10, okay? And we call this the F block. These are all going to end in F1 through F14, okay? So as you can see here, in the fourth period, after you fill 4S, then you fill 3D, then you go to 4P. So you just got to remember this low down area is, once you start going to the Ds, you've got to go back an energy level, okay? After 5S, you go to 4D, and then 5P. After 6S, these two, if you put a little kind of segment there and a segment here, this is supposed to be inserted here, okay? So you may have noticed how the numbers jump around, okay? So you go 55, 56, and then 57, all the way up to 71, and then back up to 72, okay? So the F block down here is supposed to be inserted there. They just took it out so that the periodic table would be easier to fit on a piece of paper, really, okay? So we can kind of get used to using the periodic table as a way to trace our way through electron configurations, okay? Here's something, this is not in your packet, but this is a visual that may help, okay? So you see, like, these all end in S1, these all end in S2, these elements end in P1, all these elements end in P4, and again, the energy level just corresponds to the period it's in, the row it's in, okay? The only tricky part is the D area, or the D block, where you've got to remember that if you're in, like, say, the third part of the D block, it's in the fourth row, it's not 4D, you've got to go back to 3D, okay? Again, don't worry if this seems too confusing. If you remember this from regular chemistry, great. If not, this might seem confusing, but it'll become more easy over time. Don't stress about it too much. And this is, like I said, what the periodic table should actually look like. With the F block inserted here, it makes the periodic table much longer and much harder to fit on a piece of paper. So they cut out the F block, moved it to the bottom, and smushed together the D and the S block. So that's why once you get down to periods 6 and 7, things appear to skip around. That's why. Okay. So what is the ground state electron configuration for fluorine and osmium? So I'm going to show you how I use the periodic table to do that, okay? So for fluorine, I'm taking the AP chemistry exam. I don't have this orbital diagram to look at, okay? I don't have any, all I've got to do, all I have for help is my periodic table. So for fluorine, it's right here. It has 9 electrons, okay? So I'm going to kind of use the periodic table as a reminder for the sublevels and how to get up to 9 electrons. So 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 2p5. So it's going to be 1s2, 2s2, 2p5. Okay. Osmium, much more difficult. Okay, osmium's down here. So I got to work my way up to 76 electrons. So I'm going to use these to kind of jog my memory. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 3d10, not 4d, 3d10, 4p6. Okay, so the D block is one level behind, but the S and the P are on level. So it's 4s2, 3d10, 4p6. Okay, 5s2, 4d10, 5p6. So once again, the D block was one level behind. 6s2. Now this is where things get real tricky. We jump down to the F block. Okay, so 6s2. The F block is 2 levels behind. So 6s2, 4f14, and then we're back on level. We got to get to osmium, so it'll be 5d, 1, 2, 3, 4, 5, 6, 5d6. Okay, and let me see if I'm right. Oh, it ends in 5d6. Okay. I just want to fix one thing in this wording right here. So Sometimes they number the groups on the periodic table A and B. Like sometimes they say this is 1A, 2A, 3A through 8A, and these are B's. We don't really do that anymore. So this we add to the NS, meaning like if you're in the first energy level 1S or 2S or 3S or 4S in groups 1 and group 2. Group 1, column 1, group 2 is column 2. And filling groups 3A through 8A, this means groups 13 through 18 on the AP periodic table. You're placing electrons into the NP orbitals, meaning the 2p or the 3p or the 4p. There's no 1p because the first energy level only has S, no p. But after that, groups 13 through 18 are p, okay? And in groups 3b through 8b, there they mean 3 through 12. In groups 3 through 12, the transition metals, that's what we call this section down here. Groups 3 through 12 are called the transition metals. You're placing the things into the d orbitals, and the lanthanides and actinides, that's these groups down here, because this starts with lanthanum, so these are called the lanthanides. This starts with actinum, so these are called, I always call them, I don't know, I guess they're lanthanoids and actinoids, not lanthanides and actinides. I don't know. The way I learned it is the way it's written here, but whatever. We don't talk about those much, so not a big deal. But in any case, the lanthanides and actinides, those are you're filling in the F orbitals, okay? And notice for D, it's N minus 1, okay? So you look at your energy level and you go back 1. So if you were filling the 4th energy level in the 4th row, then you go back 1 once you enter the D block. Once you enter the F block, the lanthanides and actinides, you go back 2, okay? So if you were in the 6th energy level, then you jump down to the F block. It'll be 6s2, 4f14, okay? All right, on the back, one last thing. We're going to learn about abbreviated electron configurations, okay? So you may be really sick of this. Well, you haven't had to do it too much, but you will, from writing electron configurations, get really sick of saying 1s2, 2s2, 2p6, 3, because they always start the same way, okay? And it gets very tiresome to always start the same way over and over and over again. It takes a long time to write out electron configurations. So the abbreviated electron configuration is a way, is also called the noble gas electron configuration. It's where we use an abbreviation for all the inner core electrons, okay? We abbreviate it with a noble gas because those represent, the noble gases are group 18. These kind of represent the end of filling an energy level before we go into the valence energy level or the outermost energy level. So what we do is let's say we were doing osmium and we didn't feel like writing out 1s2, 2s2, 2p6, 3s2. We would find osmium, go back, count backwards until you hit a noble gas, okay? So the last noble gas that comes before osmium, the last thing in group 18 is xenon, Xe. So we're going to use the symbol Xe to represent the first 54 electrons. So instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, instead of writing all that beginning stuff, we're just going to write Xe. And then we'll add on from there, okay? Because it's usually on only those outermost electrons that we really care about. Those are the ones that participate in bonding. Those are the ones that are excited by absorbing visible light and stuff like that. So what they did here is first they showed the full electron configuration, and then they underlined the first 54 electrons, okay, because the noble gas that comes before osmium is xenon, which has 54 electrons. And instead of writing out all 54 electrons, they just wrote Xe, okay? And then they added on from there. And they rearranged it. I don't think you have to do this. You can leave it as 6s2, 4f14, 5d6. I don't know what df. I would erase that. 6s2, 4f14, 5d6. Cross out the D. I don't know why that's there. Okay. Sometimes, even though this is the order in which the sublevels fill, because things fill out of order, so 6s filled, and then 4f, and then 5d, sometimes when they're writing the electron configuration, they rearrange it in order of principal quantum number, which is the principal energy level. So they, even though the fourth filled, part of this fourth filled after the sixth, they put the fourth first, then the fifth, and then the sixth. So that's why they changed up the order. It doesn't really matter to me which order you do it in. Okay, so go ahead and pause the video and try these yourself. Write the electron configuration. That means 1s2, 2s2, and go from there, okay? The unpaired electrons are the times when you have an arrow in an orbital, an arrow in a blank, in a spot with no partner, okay? And then ground state and abbreviated electron configuration. So the ground state's the, normal electron configuration, and the abbreviated one is the one where you use a noble gas, okay? So go ahead and try 10, 11, and 12 on your own. Pause the video and then unpause the video to check your answer. Okay, so let's start with nitrogen. Okay, nitrogen, 1s2, 2s2. Nitrogen has 7 electrons. Okay, so I need to get up to 7. So 1s2, 2s2, 2p3, and then that's it. Okay, 1s2, 2s2, 2p3. That adds up to 7. Okay. If you want to look back at a blank orbital diagram, you can, and just, use this as your guide. 1s2, 2s2, 2p3, that adds up to 7. Or you could look at your periodic table, okay? We know this is 1s2, 2s2, 2p1, 2p3, okay? For oxygen, we just need to add on one more electron, okay? So it's just going to be 1s2, 2s2, 2p4, okay? And again, those electrons add up to 8, and oxygen has 8. How many unpaired electrons are there for N and O? Okay, well, the ones in the s blank or s orbital paired up. These are paired up. Remember, P has 3 orbitals. Okay, so 2p has 3 orbitals, and this only has 3 electrons in it. So this is going to have 3 unpaired electrons for nitrogen. Okay. Oxygen's 2p sublevel or subshell is going to have 1, 2, 3, 4. Remember, we're going to put 1 in each orbital before we double up. Okay, so for oxygen, there's going to be 2 unpaired electrons. Okay. All right, ground state and abbreviated electron configurations. So carbon only has 6 electrons. So 1s2, 2s2, 2p6, and we're done. Okay. For the abbreviated, we're going to go back, 6, 5, 4, 3, 2, until we get to something in column 18. So helium is going to replace the first 2 electrons. So we're going to write He. It has to be in brackets, okay? And then add on from there, 2s2, 2p6, okay? Notice here they put the Xe in brackets to replace the first 54. Not parentheses, it has to be brackets, okay? Magnesium has 12, okay? So I'm going to use the periodic table to trace my way through. 1s2, 2s2, 2p6, 3s2, and we're done, okay? 1s2, 2s2, 2p6, 3s2, okay? If you don't trust yourself tracing this, you can always, for now, trace your way up one of these as well, okay? It's just you might not have this on the AP exam, but you'll always have a periodic table. And then for the noble gas notation, let's go back. 12, 11, 10 is our most closest noble gas when we count backwards. So underline the first 10 electrons. 2 plus 2 plus 6 is 10. Replace that with Ne for neon, and then 3s2. Okay, that's the abbreviated version. Chlorine has 17 electrons. 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 5, 3p5. Okay, 1s2, 2s2, 2p6, 3s2, 3p5. And be sure that adds up to 17. 5 plus 2, 7 plus 6, 13, 14, 15, 16, 17. Okay. And then go back, back, back. 17, back, 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 back to get to neon. So use neon to replace the first 10. And then we have 3s2, 3p5. Okay. And then vanadium right here. Okay. This one's going to go into the D block. It's going to end in D. So just remember, once you cross over it from here to here into the D block, you've got to go one level behind. So we got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 3d3. Okay. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. So that's the full electron configuration. For the abbreviated, go back, 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 back to argon. Argon's going to replace the first 18 electrons. Okay. 10, 11, 12, 18. So make this AR. Okay. And then add on 4s2, 3d3. Okay. And if you want to rearrange this, some people like to put it in order of increasing principal energy level. That's fine as well. Okay, whichever way you do it is fine. All right, so that is it for 1.5, and that is the end of your summer work. Okay, there is going to be more to Unit 1, but this is it in terms of summer work. So what we're going to do, I would recommend that you re-watch all these videos a second time before school starts, just to kind of refresh it. After you watch the videos, give yourself a chance to let it sink in. Give yourself a chance to let yourself forget some of the stuff. And maybe cover up your answers, try some of the practice problems, see if it jogs your memory, and if not, re-watch the videos maybe in August right before school starts. We will go over in class and do more practice with 1.1 to 1.5, but it'll go very quickly since you've already had these summer lessons to be introduced to the topic. And then there will be a few more lessons in Unit 1 additionally before we do our Unit 1 test. But our Unit 1 test will be very early in the school year. It will be in September, like early to mid-September. So we're going to hit the ground running. So be sure that you've done the best you can, becoming oriented to 1.1 through 1.5. Okay, and feel free to email me anytime this summer with questions, and I will see you guys in August. Bye-bye.